Hi, I'm Sarvesh Mohan.
Hi, I'm Aastik Saluja.
Hi, my name is Shikhar Govil.
Hello, my name is Tushar Vaid.
Hi, I am Saksham Bhatt. We are Team 75, all from Electronics and Communication branch. The problem we are trying to solve pertains to weed identification and management. Manual methods rely on either hand picking or spraying pesticides all over a large area. We are working to pinpoint the location of the weeds so that removal is more efficient and pesticides can be used in a more targeted manner, greatly reducing the amount needed.
Our drone based system is made up of various components. Let us see what they are.
So, starting with the frame, it is the exoskeleton of the drone and it holds the drone together and houses all the components that will be described further. So, now coming to the power module, this is the drone's heart. It distributes power from the battery to all the components, keeping everything juiced up, acting as the drone's internal power grid. Now, the ESCs, we are using 30 ampere ESCs and they are the drone's motor whispers. They receive signals from Pixhawk and adjust the power to the motors for smooth and precise flight. Now coming to the most important part of the drone, that is the BLDC motors. They are the drone's muscles. They spin the propellers generating thrust that lifts the drone and propels it through the air, acting as the drone's wind-powered engines. Another main component, that is the lithium polymer battery. This is the drone's fuel tank. It stores the energy that powers all the components, keeping the drone airborne for extended missions, acting as the drone's high-octane juice box. The propellers. They are the drone's wings. They slice through the air, providing lift and control, acting as the drone's featherly blades of precision. The Pixhawk 2.4.8. This is the flight controller and is basically the drone's nervous system. It processes sensors data and receives commands from the Raspberry Pi, keeping the drone stable, maneuverable, and acting as the pilot in the cockpit. Now, the GPS module. This is the drone's map and compass. It tells the drone its exact location and helps it navigate precisely, acting as the drone's trusty GPS guide. Buzzer module. This is the drone's voice. It beeps and buzzes to give you important alerts like low battery or mission completion, acting as the drone's friendly chatterbox. Moving on to the next component, safety switch. This is the drone's emergency brake. It instantly cuts the power to the motors if anything goes wrong, keeping both the drone and the environment safe, acting as the drone's guardian angel. The FSI-6B receiver module and transmitter module. The receiver acts as the drone's ears, listening to the commands from the remote control and relay them to the Pixhawk like a walkie-talkie for the drone. So, the Raspberry Pi is basically a tiny powerhouse, and it is the drone's brain. It runs a deep learning algorithm that identifies the weeds in real time, guiding the drone's mission like a skilled AI co-pilot. The day and night USB vision camera. This is the drone's eye in the sky. It captures the video footage of the field, feeding the weed identifying algorithm on the Raspberry Pi, acting as the drone's eagle-eyed scout.
Now that we have explored the hardware components involved, let us see how these are connected. Pixhawk to Pi. The Pixhawk controller is serially interfaced with Raspberry Pi using 4 cables. These are VCC, ground, serial data, and serial clock. Next is Pixhawk to peripheral. The controller is connected to the various peripheral. These include GPS, power module, receiver, ESCs, safety switch, and buzzer. Coming to LiPo battery to power module, the battery provides power to the power module from where it is distributed further. Coming to base plate to ESCs and power module. The 4 ESCs and the power module are soldered onto the base plate. This base plate acts as a power distribution circuitry for the drone. Next is ESCs to motor. The ESCs are connected to their respective motor. The orientation of the connection decides the direction of the rotation of the motors. Pi to camera. The Raspberry Pi is connected to the camera using USB 3.0 port. Lastly, Pi to power bank. The Pi receives power from the power bank via USB-C type port.
Discussing the software involved, the software aspect of this project can be broken into three main portions: the drone movement, weed detection, and mapping. Let us explore each part to see how it all comes together. The drone's movement is orchestrated by a Python script utilizing the DroneKit library. This script, when fed the farm's dimensions as parameters, generates a flight path optimized for area coverage. The script interfaces with the drone's autopilot system, sending waypoints and control commands. Altitude hold and precision positioning are all handled autonomously, ensuring efficient and safe flight. Weed detection relies on the YOLO V8 model, a deep learning architecture trained on a meticulously curated dataset of 1100 weed and crop images. This model, integrated with the OpenCV library for image processing, analyzes live video footage streamed from the drone's camera. Upon detecting a weed, YOLO V8 generates bounding boxes and the Raspberry Pi fetches coordinates from the GPS module. At the mission's conclusion, the stored weed coordinates undergo a final transformation. Utilizing the Google Maps API, they are transmitted to a dedicated web application. This application builds a real-time geospatial map, visually representing the detected weeds and the precise location within the field. This map, accessible remotely, serves as a valuable tool for analysis and decision making.